Okay, so cool. Let's jump in with the content. I think today's lesson is going to be pretty fun. I hope you really like it. Last time we talked about discrete probability spaces and random variables. So again, we're sort of building up this idea of creating a mathematical model that represents the idea of a random experiment in some way that's mathematically useful in that it allows us to translate questions back and forth between the real world random experiment situation and the mathematical model. And we drew some conclusions. For example, we decided that our probability space should consist of a set omega together with what other mathematical object to represent the probability. All right, cool. So some good answers there. The probability mass function, that's one way of thinking about it, or the probability measure capital P, that's another possible answer to this question. Those are both good. So just to review, so we have this function little m, which is our probability mass function, and that maps each element of our sample space to some real number between 0 and 1, and it does so in such a way that as we total those values up over the whole sample space, we get 1. Alternatively, we could take the perspective that events are more important than elements of the sample space, and therefore we should focus on the function that takes an event as input and returns the probability of that event, which also is going to be an element of the interval from 0 to 1. And the connection between the two is that to compute the probability mass associated with an event, we total up the individual probability masses of the elements of that event. So this notation, if you're not super comfortable with sigma notation yet, it just means find m of omega for each of the little omegas in the event E in question, and then total them up, just add them up. So that notation just means exactly this. Okay, here's a question. Is a random variable an example of a sample space or a probability mass function or probability measure or none of those? All right, so the correct answer here is none of those. The idea of a random variable is that it's just any function, any real valued function on the sample space omega. So any function from omega to r. And the same can't be said of any of those other objects listed. The closest one is probability mass function, because that is also a function from omega to r. But it plays a different role because it's describing the probability of each outcome rather than being some sort of payout or numerical result of the random experiment. And also as a class, it's quite different because it has this constraints. It returns non-negative values, it sums up to 1. And random variables have none of those constraints. It's just any numerical result associated with the outcomes of the random experiment. That's it. So random variables are a new idea when we get to that point in the curriculum where we've only talked about sample spaces and measures. Random variable is going to be a fresh thing. Here's yet another review question from last time. So what's the difference between a random variable and a distribution? So this one is excellent from Hardy. So I really like this formulation of it. Hardy, do you want to tell us about your answer here? Yeah, exactly. Yeah, that's perfect. So this is what I'm going for here with this particular question and with this visualization. I want you to sort of have something to hold on to when you think about the difference between these things, so something to hold on to visually as a sort of mental image, because otherwise it's very easy for that idea in your head to kind of wash out over time, sort of shortly after you learn these distinctions. And I'm hoping this mathlet will kind of help stick in your head for you. So the idea is we have a random variable, in this case, the total number of heads in 2 coin flips. And it associates, for example, TT, there's no heads there, so that goes to 0. And so the random variable is this set of orange arrows, if you will. It's telling us for every one of these outcomes what the numerical result associated with that outcome is. And once we decide what our random variable is, we get its distribution as a result. Because what we can do is push every probability mass forward from this side. So each one of these represents a quarter mass. And then we just see where it sits on the number line. And then at this point, we've forgotten, and I kind of changed the mathlet up here to make this more clear relative to last time. Once we compute the distribution, we've forgotten completely about what went where. So we don't know that this quarter mass came from TT if we're just asking what's the distribution. All we know is a quarter mass here, quarter mass there, and a half mass here. That's it. So that's our probability measure, which is the distribution of this random variable X. So to draw out this distinction in terminology, a probability measure is any object that tells you where the probability mass is. So for example, a probability mass function communicates a probability measure for you. So you could say quarter mass here, half mass here. That's it. That's the probability measure. Distribution relates that measure to the actual random variable. So the term distribution, the role of that word is to actually relate the random variable with a particular probability measure. So we say this probability measure represented by this image is the distribution of this random variable X. So that's the distinction for me between measure and distribution. The measure is anything that says where the mass is, and a distribution is something that specifically pertains to a random variable. You want to talk about a distribution of a random variable in order to be strictly sticking to the textbook definition of the terms. In reality, people often use distribution to mean measure, but I will sometimes be quite careful about that. Anyway, this is a picture I want you to have in your mind. The random variable is the orange arrows, the sort of motion left to right that associates outcomes of the random experiment with some particular numerical output of interest, in this case, number of heads. And the distribution is just where these masses are sitting over here on this number line, quarter here, half here. That's the full information. In some sense, this is even a little more information than you really need for this distribution, because you don't actually know once you see the distribution that this came from two different inputs. Like in the picture, you can tell, okay, here's one, here's another one. In reality, all you see is that there's a total of a half here. So that half unit of probability at the level of the distribution, you might think it could have come from just a single element of the sample space over here. So the point is just how much mass is there at each point, like where are the masses? That's it. That tells you completely what the probability measure is. And that's our distribution for this particular random variable X. So I want to get maybe slightly philosophical a little bit to try to put this in perspective. You probably have had some contact with probability in the past in which all of this stuff is completely elided. Like, why do we care about this sample space omega? Like, by the time we map everything over here, we have our distribution. You can answer probability questions about the experiment just based on the distribution. We don't actually have to see omega. Once we have the distribution, that's enough to answer any question you might have about this random variable X. So like, why do we care about the relationship with omega? Let's just talk about distributions and call it a day. And I want to suggest the reason that we don't do that. So in the real world, we're almost never looking at just one random variable. We're interested in how random variables relate to one another. That's really the essence of data science. You're trying to make some sort of prediction or gain some sort of understanding of the structure of a data set. And that always consists of understanding joint relationships between multiple random variables. For example, how does the smoking variable, like does a person smoke or not, or maybe how much do they smoke? How does that variable relate to the lung cancer variable? Did they get lung cancer or not? Or variables like lower interest rates, unemployment, S&P 500, and the Dow Jones. These are sort of economic financial variables that you can measure, on a given day or quarter or whatever. And you can ask, how do they relate? If one goes up, does the other go down? That sort of thing. These are really important questions, of course, and in some sense, nearly every question about data science cashes out to a question about relationships between random quantities. And even in the instance where you really just care about one number, like you're an insurance company and you want to know how much money are we going to lose if the hurricane veers west instead of east. And that you could think like that's a single random number, yet it's composed of many smaller random variables. So you still need to understand relationships between those smaller random variables just to understand that one big one. So this idea of relationships between random variables, it's really at the crux of everything you do as a data scientist, at least when it comes to building predictive models or understanding the structure of a data set. And mathematically, the way we capture those interactions or those relationships is by realizing the different random variables as functions on a common probability space. So the relationships are going to be sort of embedded in the way that the random variables map specific outcomes to the numerical results associated with that outcome. So for example, the random variables, 1 if the first flip turns up heads, 0 otherwise, and 1 if the second flip turns up tails and 0 otherwise, those random variables have a different relationship than they would if instead of the second flip, we looked at the first flip for that second random variable. And the way that those relationships are captured in probability theory is that we write down this explicit relationship between the random variables and the probability space. We say for every outcome in the sample space, where does that get mapped to by this random variable? And we'll be able to use that information to get a really good handle on how to visualize the differences between these things. And we'll get to that today. Incidentally, I want to mention that this idea, 1 if an event occurs, 0 otherwise, that's kind of a mouthful. And it's really important. This comes up a lot as we kind of work through the nitty-gritty details of probability. And so we give this a name. It's called the indicator random variable of an event. So given any event, we can associate with that event an indicator random variable, which morally speaking just is the event. Like an event is something where we can say, okay, for this little omega, it didn't occur, that's a 0. For this other little omega, it did occur, so that's a 1. You can think of the event and the indicator random variable as totally interchangeable. It's just a question of whether you realize it mathematically as a subset or as a binary function on the sample space. So maybe I'll pause for a moment here and see if some questions have come in. I think the answer is no. Okay, well, feel free to send a question in. By the way, as a few people have learned recently, you should feel free to ask questions as we go, even if you suspect that I'm not going to get to them or answer to them, because what I can do and what I do is go back after class through the questions and respond to individual people. I can find your question, I can click on it and open up your private chat and send you a response in a way that you can see what you asked and you also see my response to it. And then I can also click an email button that sends you a notification about that. So do feel free to ask me questions, even if you feel like I'm probably not going to be able to get to them in class. Okay, I want to talk about a slightly different topic, which is closely related, which is another way to visualize these probability measures on the number line. So we've talked about the stick plot approach, where we just say, okay, if there's some amount of probability mass at -0.5, we'll put a little stick there whose height is equal to how much probability mass there is at that location. Same idea for these other two. So this is a random variable that has a pretty decent chance of being -0.5. It's got a smaller chance, but still positive, of being 0.2. And if it's not one of those, then it's definitely 1. And it can't be anything else. It's going to be definitely one of those 3 values. That's what this stick plot means. And stick plots are not the best visualization for every situation. They are very helpful. They have some advantages over other visualizations in certain situations, but you want to sort of widen your arsenal here. And this is a really good one to add to it. So we'll see some very cool things about the cumulative distribution function. But the idea is we're just going to make a graph out of these stick plot diagrams by just sort of picking up the mass as we sweep from left to right. So when we're way over to the left, there's no mass to our left. And so we're down here at 0. And then as soon as we hit that first probability mass, we jump up. We gobble that mass up and our graph jumps up to this level, which is exactly the height of that stick. And then when we eat another one, then we jump up by that amount. So this height here is equal to what that shorter stick height was. And then of course, we're going to take another big jump here when we hit this one. So this is the cumulative distribution function. It's the function which associates with each value x, how much probability mass is at or to the left of that value x. So I made this mathlet because I think it's really important to kind of get this dynamism down in your head, this idea of sort of gobbling up mass as you move from left to right. And there's some things that can be a little counterintuitive about the cumulative distribution function. So I want to ask some questions to try to focus in on that. So if you're looking at the CDF of a random variable or of a distribution, how can you tell where lots of probability mass is for the underlying probability measure for this orange graph right here? All right, cool. So most folks got that. That's really good. So the answer is where the CDF increases the most. So for example, if you look at this picture, if we move way over to the right here, the CDF is very large over here at 2.5. It's actually equal to 1, which is the biggest a CDF can be. Yet there's no probability mass over here. There's no probability that the random variable is even anywhere close to this value. And it's going to stay at 1 forever. So if we want to see where the probability mass is, that's where the graph jumps. So the CDF is gobbling up the mass as you move from left to right. So the mass is where the CDF jumps the most. Okay, here's another question to kind of check for understanding. So let's say to find the CDF of the sum of two random variables, we're just going to add the CDFs of those random variables. Does that work, or is that the wrong thing? So I think this question kind of illustrates the importance of thinking carefully about what the values along the two axes represent. So remember, when we look at a CDF, the vertical axis represents probability. So that's true for the mass function and for the CDF. Any particular y value in this diagram represents an amount of probability mass. But when we add random variables, we're not adding probability mass at all. The amount of probability mass stays the same, and it's all in the same places. So you can see this if we look back at this figure. So we have these probability masses here. They're going over to particular places on the number line, but the outputs here are depicted horizontally. And when we're adding random variables, things are getting added along this particular axis. So for example, if we think about the number of heads in the first flip, these two outcomes would both map to 1, and these two outcomes would both map to 0. And if we ask how many heads are in the second flip, these two would both map to 1, and the other two would both map to 0. So these random variables are both at 0 and 1. All the masses would end up at 0 and 1. And yet, when we add the random variables, we'll get a 2 here from this 1 plus 1 that happens for this little omega. And so the mass actually ends up further to the right. So when we're adding functions in this figure, things are getting added sort of in a left to right kind of way. We're not adding probability mass. The probability masses end up in different places on the number line, depending on how that sum shakes out. But there's no sense in which we're adding probability masses here to add random variables. So one of those sums happens in the horizontal direction, and the other one would happen in the vertical direction. So let's provide a kind of direct answer to this question. That maybe the easiest way to see that you can't add CDFs is that a CDF approaches 1 as the input goes to infinity. The further you go to the right, the more of the probability mass you've gobbled up. Eventually, you've gobbled all of it up, or almost all of it up, and you're way up here at 1. So that's going to be true for both CDFs. And if we just add them as functions, that means that we're going to be, instead of leveling out at 1, we're going to level out at 2. There's going to be 2 total units of probability mass that get eaten up by the 2 cumulative distribution functions together. And that's not right. You can't have a total probability of 2. And then the other sort of a different way of thinking about this to see the answer is to observe that, as we just discussed, if you have number of heads in the first flip and number of heads in the second flip, those are doing all of their jumping at 0 and 1. So all the probability mass is sitting at 0 and 1. And yet when you add them as random variables, you get a 2 in there, and there's no jump at 2 in either of the original CDFs. So the relationship between adding random variables and CDFs is a little bit tricky. It's going to require more thinking. We'll do some of that thinking later. Just want to set the stage that this is a different thing when you're adding random variables or otherwise combining random variables, and when you're looking at the CDF. All right, there's one more message part of that explanation. Okay, so I think this next section is where a lot of these ideas will start coming into better focus. So we're going to really build up a powerful tool for appreciating how random variables relate to one another. So this is kind of a continuation of the discussion from a few minutes ago, where we said that we're usually interested in the relationship between multiple random variables. So let's look at a way of doing that brings a little more focus to the problem than just saying, well, we realize them as random variables on a common sample space. We want to draw a picture that actually tells us what's going on. But at the same time, that picture needs to convey more information than just the individual distributions of the two random variables. Let's think about, we talked about this last time, but now here's a mathlet for it. Let's think about total number of heads and total number of tails, those two random variables. So as we discussed last time, they're going to have exactly the same distribution. There's going to be a quarter unit here, half unit here, quarter unit here. That's the same for both of them. But as random variables, they're different because those probability masses come from different parts of the probability space. So TT goes here. Oh, I messed up the arrows. The arrows are the same in the two diagrams, and they shouldn't be. If you look at where the masses actually go, that's correct. So TT goes over here to the end, and HH goes here to the beginning. I'll fix that in the script after class. But in any case, you can see how they have the same distribution despite being different random variables. So that's telling us that the individual distributions of the two random variables are not enough to capture the relationship between the random variables. All it tells us is that the individual distributions are the same probability measure. And this idea of the distributions of each random variable considered in isolation of the other random variable, this is an important idea, and we often want to draw this distinction. And in that case, we call these marginal distributions. So marginal distribution is just a distribution of one random variable in a situation where there are other random variables that you might want to consider that random variable's relationship to. So it's sort of a weird term where marginal distribution just means exactly the same as distribution, but you use it in a particular context to draw a distinction with another kind of distribution you might otherwise be looking at. So the key idea that we're going to use in order to kind of rise above this, to capture joint information that's not contained in the two marginal distributions, is to take every probability mass, and instead of mapping it to a number line, we're going to map it to the plane. So we're going to have two random variables, X and Y, that we want to understand the relationship between. In this case, it's going to be number of heads, number of tails. And we want to map all those probability masses. Each probability mass goes to the point X comma Y for that probability mass. So that outcome is associated with a particular X value and a particular Y value. Put those together in an ordered pair. That's where that probability mass goes. So we're going to end up with a probability measure on the plane. I want to try a kind of new sort of exercise, if it works, where we try to do this by grabbing things and dragging them. So you should be able to grab individual objects here on your canvas and move them in the plane where they go. So X should be number of heads, Y should be number of tails, and these particular elements of the probability space, you can just drag them over here and put them where they go. Very nice. So people are for sure getting this right. That's great. Right. So just for completeness, even though everyone who's submitted has gotten this right. So HH goes here because we have 2 heads and 0 tails. Both of these go here, and you could maybe offset them a little bit so that you can still read them. You know, this is just a kind of editorial decision here. Obviously, they should go in exactly the same point in principle. And then this one goes here. So, you know, in some ways, maybe I should have made these more sort of like change the opacity of these so that it's kind of less, there's less visual interference. But anyway, you get the idea. Here's how it should go. Insert that and send it. Okay, here we go again with the start. I still have to think of a good solution to this problem. But anyway, very nice job. Yeah, getting this right. I maybe just want to throw in an extra question here, which is, do you like this kind of exercise where I give you things, you can kind of drag them around and submit an answer that's an image? Okay, great. So there's some good enthusiasm there. It was not possible until recently. I had to create that functionality and depended on a bunch of other things. So I'm thinking I might recast a lot of the drawing questions that I already have from last year and make them more like this. Okay, in any case, I didn't draw in the script. I made a mathlet instead. Same idea though. So all the points go to, all the masses go to where in the plane they belong. So the X comma Y. So both of these go to 1 comma 1, and then each of these goes to 0, 2, or 2, 0 respectively. And so what you end up with here is a quarter mass here, a half mass here, and a quarter mass here. So it kind of expands it out into the plane, the sort of 2 marginal distributions that we had before, and it tells us kind of something interesting. about how these random variables are related. This is very visually striking. You see this sort of diagonal shape. And this is called the joint distribution of X and Y. So the probability measure on the plane, which tells you where your probability masses are sitting in the plane. We call that the joint distribution of X and Y. So again, distribution is essentially a synonym of probability measure, except that distribution emphasizes the role of the random variable, or in this case, the pair of random variables, X comma Y. So one thing that's really nice about this visualization, and we'll be able to see this kind of structure in many instances where we're studying two different random variables and we want to see how they're related to one another. We can see that in this case, for example, they're negatively correlated. So we haven't defined that term here, but from other experience, you probably see this kind of structure in the plane and you're like, oh, one goes down when the other goes up and vice versa. That's a negative correlation. There's some negative relationship somehow between these two. And of course that makes sense because if you have more heads, you'll have fewer tails and vice versa. That's really popping out in this representation of this joint relationship though. Okay, so here's a check for understanding question about these joint relationships, or about the idea of a joint distribution. What can we say about the probability masses if we look at the joint distribution of X and X, where X is just any random variable on any probability space? So obviously there are various possibilities here, but what can you say to kind of narrow down the space of possibilities of what you would get for the joint distribution of a random variable and itself? Okay, great. So some good thoughts that people had sort of explaining the way they were thinking about this. And I think it's maybe worth elaborating on a little bit to make it clear what's going on here. So we're talking about the joint distribution of X and X, where X is some random variable. It might help to focus on a specific example and then think about how that situation is actually general, or the conclusions that we'll draw will be general. So I'll try my drawing tool here. We have our joint distribution. It's going to be in the plane. So here are our axes. And let's think about, again, this random variable that's like total number of heads in this 2 coin flip experiment. So it's going to have a possible value of 0, 0, because we could get no heads, and that's going to be a quarter unit of mass. If we get a head, if we get one head in total, that has a 1/2 probability of occurring, and we would get a 1 on both axes because we're plotting X, the outcome of the X random variable on both axes. So we're going to get a 1/2 unit of mass at 1, 1. And then we get another quarter unit mass at 2, 2. Because there's a quarter probability that X is equal to 2, in which case X comma X is equal to 2, 2. So that's sort of what's going on here. And what you can see is happening in this case, and also is inevitable in general, is that all the masses are going to lie along the line Y equals X. And otherwise you can't say anything. The masses could be anywhere along that line. They just total up to 1. But what you know for sure is that you don't have any masses off that line. Yeah, so here's just a message saying the same thing. All the probability masses lie along the diagonal line Y equals X. Okay, so I'm pausing for a moment because I'm considering there's a question that I'm thinking about whether it's worth fielding in class. And then there's also a comment from the last one that I think is really more helpful than anything that I've said so far for drawing out what's going on. So yeah, let me share that anonymously. So here was one of the responses. And I think this is really useful. When you think about X and Y, sort of plotting them on separate axes, and then you think about somehow the two axes being the same as each other, it feels weird. It feels like, no, they're orthogonal. So they should be kind of, on the random variable side, they should be independent or something like that. And if they're the same, then they're really not independent. And it's super weird to be plotting them on orthogonal axes. The thing is that really is sort of bears emphasizing in this case is that we're not saying anything about X and Y, or rather the two random variables we're plotting on the two axes. We're not saying anything about the relationship between those two random variables when we decide to plot their joint distribution. The relationship emerges from the joint distribution when we plot it in the plane. So for example, here, maybe we didn't know X and X were equal at the beginning. and then we plot this joint distribution, we're like, oh yeah, this all lies on the line y equals x. So actually, that's telling us something about the relationship between these two. Or up here, the fact that they lie on this line, that relationship between the two random variables emerges from plotting the joint distribution. We don't require anything about the random variables in order to be allowed to plot the joint distribution in the first place. So we can do that for any pair of random variables. Okay, here's another question about random variables and joint distributions. Can the marginal distributions of two random variables be worked out if we know their joint distribution? Or do we need to go back to omega to find the marginal distributions? So we know we can't get joint distributions from marginal distributions, but can we go the other way or not? Okay, so I think we haven't heard from Yuetian in a while. So this is her answer. Do you want to tell us what your idea is for how to recover marginal distributions from the joint distribution? Yep, that's great. That's exactly right. So the point is that we have all this information about x comma y. And whenever you know x comma y, you know x and you know y as well from that. So it's more specific information. We can totally recover a marginal distribution from a joint distribution. So let's take a look at this example where we have these outcomes here mapping to where they go under the joint distribution, under the rule for recovering a joint distribution from information about where all of the elements of the sample space are sent. And then let's say we want to get the distribution of x from this. Well, we know that because this quarter mass is here, that in particular, its x value is 0. So we register a quarter mass of probability at 0. And same thing for the other two. If you want to visualize this, you can imagine smashing all of the probability measures down from wherever they are in the plane to the x-axis. So just projecting to a common axis. And you might have to add stuff up. So here it's not like that. So every vertical line only passes through one mass. So we're just moving the masses. If you had multiple masses along the same vertical line, those masses would add up. But otherwise, that's it, that we can get from the joint information down to the individual marginal information just by projecting things down. And similarly, I don't have a slider for it, but you could project things down to the y-axis and recover the marginal distribution of y. So I want to throw in a quick side note, just giving you a piece of terminology that I will sometimes like to use, which is support. So the support of a probability measure is, roughly speaking, it's where the probability measure has some mass. So for example, this probability measure has mass at 0, 2, and 1, 1, and 2, 0. So that 3-element set is the support of that distribution. So that's just a convenient way of saying where the probability measure has mass, and there's loads of space where it has no mass. Like if I ask what's the probability measure of this set, like some kind of oval cutting through here, the total probability measure associated with that set would be 0. There's no mass in there. So the idea is if you look off the support, then in that whole space, you're going to see no mass. So we talked about this a little bit with marginal distributions or with distributions of a single random variable. And the same thing is true for joint distribution. So a joint distribution is enough information to answer any question you might have about the probability of any event, as long as that event only involves those two random variables. So who knows if there's some third random variable involved. But if you just want to talk about x and y, the joint distribution of x and y is complete information for answering any of those questions. So what is the probability of the event capital X greater than capital Y in general? What would we do with the joint distribution in order to answer that question? Okay, so we have some answers here that are good. So we look at the mass beneath the line y equals x, since those are the outcomes that correspond to x being bigger than y. A couple other answers essentially saying the same thing, so that's good. Yeah, so I'll maybe draw that just to have a picture down. So this is the line y equals x. This is the region where x is bigger than y. And so we just add up the mass over here. So you add up all the masses in this region. Anyway, that's the picture you want to have in mind. And one thing that a few people commented on that I think is worth mentioning. So some people were like, well, let's look at the marginal distribution of each one and work from there. One thing that's helpful to note is that you cannot answer this question from the marginal distributions alone. So we have to keep the joint distribution in order to know for any given probability mass in the picture whether it's above or below that line. So if you had a probability mass that was, well, yeah, maybe I'll refrain from further explaining that point. You can experiment with it a little bit and come up with an example where you get different answers to this question. What is the probability X is bigger than Y, even though the marginal distributions are the same? So you come up with sort of one XY pair and another XY pair where the marginals are the same for X and for Y in the two examples, yet the joint distribution is different and this question has a different answer. So that's possible to do. You can kind of play around with some different configurations of mass in the plane and work that out. So I won't try to do it in real time, but that's possible. It does illustrate a valuable point here, which is that when you want to think about what's the space of possible joint relationships between two random variables, that question is answered by just any sort of layout of masses in the plane that you might want to dream up. So just give yourself a blank pair of axes. Imagine that you're the deity of this little universe and you have a unit of probability mass like Play-Doh in your hand, and you can just put the mass down however you want in the plane. You can break it up into tiny little pieces and sprinkle it all over the place. You can pile it all up at one point. You can put it at, a few different points. As we'll see later, you can also smear it out over a continuous region. But that's sort of capturing that kind of mental image of like you have a unit of Play-Doh representing probability mass. There's a plane before you, and you can just put that mass wherever you want in the plane. That picture is representing the full space of possible joint relationships that any two real valued random variables can have with one another. So you can use that perspective to kind of experiment with questions and answer and come up with answers to those questions without having to go all the way back to the random experiment and try to cook up some interesting random experiment that has certain properties. Forget the random experiment. You've got a unit of mass, throw it down in the plane however you want, and you can kind of play with that. You've got more geometric intuition, and your geometric intuition suggests the full flexibility you have in deciding how that probability mass is laid out. And that's 11 o'clock in 0 seconds. So I'll stop there. I'm right up against the conditional probability section, which is where we're going to go next. And so I think this is a really good stopping point.